Okay, so let's continue our discussion of Banach spaces. So let's recall the definition. By definition, a Banach space is a complete normed space. Complete here means that, as usual, as in the case of metric spaces, this means that each Cauchy sequence converges. At the previous lecture, we gave some basic examples of Banach spaces. In particular, we proved that each finite dimensional normed space is a Banach space. Also, we know that if you take any set x, then the space little L infinity of x, which consists of all bounded functions on x, is also a Banach space. Let's recall that the norm here is just the supremum norm. If now x is a topological space, then we can consider the space CB of x, which consists of all continuous bounded functions on x. And we know that this is a closed vector subspace in L infinity. So this is also a Banach space. Exercise sheet 2 contains some other examples. Let me mention just some of them. For example, if we take the space little c0, which consists of all sequences which vanish at infinity, then little c0 is a closed vector subspace in the space of bounded sequences. And so it is also a Banach space. Also, if you take the space Cn of AB, which consists of all n times continuously differentiable functions on the interval AB, let's recall the standard norm. The standard norm on the space is given by the following formula. So we consider all derivatives of our function f from 0 to n. We take the supremum norm of each of them, and then we take the maximum. So this is the standard norm on Cn of AB, and it's a useful exercise to show that this is also a Banach space. So these are useful exercises. Okay, so today our first goal is to show that the space little LP is a Banach space. Let's recall the definition. If P is a real number between 1 and infinity, then we define the little LP space to be the space of those sequences xn such that the following series converges. And the norm on the space is defined as follows. So we know from first lecture, we know that this is a Banach, we know that this is a normed space. So now we want to show that it is complete. LP is a Banach space. For all P, including infinity. Well, if P equals infinity, we already know that this is Banach space. This is the space of all bounded functions. So now we have to show that it is complete if P is finite. Okay, so let's take a Cauchy sequence. xn, a Cauchy sequence in LP. So each xn is an element in LP. So it has the following form: xn1, xn2, and so on. So the superscript here refers to the number of the element in the sequence, and the subscript is the number of the coordinate of the respective element in LP. So this is a Cauchy sequence. Well, now let's observe the following. If we take any natural number k, then we have the following obvious estimate. For each and m. Well, this is clear. If we look here at the definition of the norm, clearly each coordinate of x is less than or equal to the norm. So we have this inequality. But xn is a Cauchy sequence, and this estimate readily implies that the sequence of coordinates for fixed k is also a Cauchy sequence. X and k, where k is fixed and n runs over the natural numbers. This is a Cauchy sequence of numbers, a Cauchy sequence in the base field k. Since the field of real numbers and the field of complex numbers are complete, we conclude that this sequence converges. X and k converges to some number that's denoted by ak. So for each k we have a number ak, and so we get a sequence a1, a2, and so on. So as a result, we see that our sequence xn converges to A pointwise. Of course, this is not the end of the proof, because to complete the proof, we have to show that this sequence actually belongs to LP, and that xn converges to A with respect to the LP norm. So we want to show that A belongs to LP, and that xn converges to A in LP. Okay, now to prove this, prove these facts, let's write explicitly the condition that xn is a Cauchy sequence. So for each positive epsilon, we can always find a natural number, big N, such that whenever little m and little m are big enough, we have the following inequality. This is just the definition of a Cauchy sequence. Okay, let's now do the following trick. So this norm is the sum of an infinite series. Let's now consider finite sums from the series. So we take an arbitrary natural number big K, and we have the following inequality: the sum from 1 to big K, xin minus xim to the power p is less than or equal to epsilon to the power p. So for convenience, I just took the pth power of both parts of this inequality, and I consider only the finite sum from 1 to k. Okay, now we do the following trick. We fix a little n, and we let little m go to infinity. This is a finite sum, so we can always take the limit. And we get the following inequality: xin minus ai to the power p is less than or equal to epsilon to the power p. And that's this. So we get this inequality as m goes to infinity, and this holds whenever little n is bigger than big N. And the k is an arbitrary natural number. Okay, now we see that this estimate holds for an arbitrary natural number k. So we can now let big k go to infinity, and we conclude that since this holds for every k, we conclude that this series converges, and the sum of this series is less than or equal to epsilon to the power p. And again, this is true whenever little n is greater than big N. In other words, this inequality means that the sequence xn minus a is an element of the little p space, because the sum is finite. And moreover, the norm of this, the LP norm of this sequence is less than or equal to epsilon. This is just an equivalent form of writing the same statement. And this holds for the same little n. Okay, so that's it, because this readily implies that little a is also in LP, just because we can write it in the following form: xn minus a. So this is obviously true, but this is an element in LP, and this is also an element of LP. But LP is a vector space, so we conclude that a is also an element in LP. And we know that whenever little n satisfies this inequality, we have this. But this means precisely that xn converges to a in LP. And this completes the proof. Okay, in fact, the more general result is true. I have the following effect. For each measure space, omega, the big LP space, LP of omega mu, is a Banach space. For each measure space omega. I'm not going to prove this result for the following reason. In the case where p equals 1 or p equals 2, this fact is usually proved in measure theory courses. If p is a real number between 1 and infinity, then the proof is essentially the same as in the case where p equals 2. So the details of the proof are exactly the same. So you can just take your favorite proof of the completeness of the big L2 space and observe that the same holds for the big LP space. And in the case where p is equal to infinity, this is a simple exercise which will be included in the next exercise sheet. Okay, so now let's now look at the space of bounded linear operators. Let's recall that if you have two normed spaces, x and y, then the space of bounded linear operators from x to y is a normed space. So the natural question is, when is it complete? And here's the answer. If x is a normed space and y is a Banach space, then the space B of xy of bounded linear operators from x to y is a Banach space. So it's essential here that y is complete, and x can be arbitrary. Okay, let's try to prove this result. So we take a Cauchy sequence, Tn, a Cauchy sequence in B of x, y. To show that it converges, let's first of all show that it converges pointwise. Well, indeed, if we take an arbitrary element little x in x, we have the following simple estimate. Tn of x minus Tm of x is less than or equal to the norm of Tn minus Tm multiplied by the norm of x, just by the definition of the operator norm. So now Tn is a Cauchy sequence, and this is a constant, x is fixed. So this inequality implies that Tn of x is a Cauchy sequence in y. Tn of x is a Cauchy sequence in y. But y is assumed to be a Banach space. So this sequence converges to some element in y. Tn of x converges to an element which will be denoted by T of x in y. So this is true for any element little x in our space. And so we obtain a map. So we obtain a map T from x to y, which is the pointwise limit of the sequence Tn. Well, now it's a simple exercise to show that T is linear. It's a simple exercise that the pointwise limit of a sequence of linear operators is a linear operator. So now what we want to do is to show that, first of all, T is bounded. That is, it belongs to the same space, B of xy. And we want to show that Tn converges to T in the normed space B of xy. Again, we will do the following. Let's write once again the assumption that the property that Tn is a Cauchy sequence. So by assumption for each positive epsilon, there is a natural number n, such that for each little n and little m, bigger than this number, the distance between Tn and Tm is less than or equal to epsilon. Okay, now let's recall the definition of the operator norm. So the operator norm is the supremum of Tn of x minus Tm of x over the unit ball of our space. So this implies that if you take an arbitrary vector x in the closed unit ball, of x, we have this inequality. So now we take any x in this ball, we take any little n in here, and we let little m go to infinity. So now we know that Tm of x converges to T of x, and if we take the limit over m, we get the following. Tn of x minus T of x is less than or equal to epsilon if n is bigger than big N. So this inequality, so in particular this holds for each vector x in the ball. And by the definition of a bounded operator, we conclude that Tn minus T is a bounded operator. Tn minus T is a bounded linear operator. And the norm of this operator is the supremum of this over the ball. So we take the supremum and we see that the supremum is also less than or equal to epsilon. And again, it holds for n for each little n satisfying this condition. Okay, now since the space of bounded linear operators is a vector space, we conclude that T is bounded because T can be written in the following form. This is bounded. This is also bounded. So T is bounded. And this condition here means exactly that Tn converges to T with respect to the operator norm. Tn converges to T in the normed space B of x, y. So B of x, y is complete. Okay, by the way, let's look at the proof once again. And let's observe that we use here essentially the same pattern as in the proof of the completeness of the little p-space. And in fact, the same pattern is used in the proofs of the completeness of almost all classical Banach spaces of functions or of operators. So explicitly, the pattern is as follows. We take a Cauchy sequence in our space. And first of all, we observe that it is pointwise Cauchy. If we look at the proof of the completeness of the little p-space, this was exactly the first step. So we take a Cauchy sequence, and we fix the number of the coordinate, and we observe that this sequence is also a Cauchy sequence in K. And the same trick was done in the proof of the completeness of B of x, y. So we observe that our sequence is pointwise Cauchy. This implies that there is a pointwise limit. In the case of the little p-space, the pointwise limit exists because of the completeness of the base field. And here the pointwise limit exists because of the completeness of y. So our sequence converges pointwise. And now to show that it converges in respect to the corresponding norm, we use once again the assumption that it is a Cauchy sequence here and here. We wrote explicitly that the sequence is a Cauchy sequence. And by using this condition, we proved that the limit, the pointwise limit, which was found at the previous step, the pointwise limit, belongs to the same space, And the sequence is norm convergent. The sequence is not only pointwise convergent, but is in fact norm convergent. So this is the general pattern, or the plan of the proof. And so if we want to prove the completeness of some function space, or of some space of operators, this is the standard plan. So first of all, you find a pointwise limit, and then by using the Cauchy condition, you prove that actually this pointwise limit is in the same space, and the sequence is norm convergent. Let's now prove a simple but useful property of Banach spaces, the so-called extension by continuity theorem. Extension by continuity. Suppose that we have a normed space X. X is a normed space. And suppose that X0 is a dense vector subspace. Also suppose that Y is a Banach space. Y is a Banach space. And suppose that we have a bounded linear operator, T0, from X0 to Y. So we have a bounded linear operator defined on a dense vector subspace of X. Then, first of all, I claim that this T0 can be uniquely extended to X. There is a unique bounded linear operator, T, from X to Y, which extends T0. Moreover, the norm of T is the same as the norm of T0. And finally, if T0 is topologically injective, or if it is isometric, then so is T. The proof is more or less straightforward. So we take an element in X, and we want to define T of X. So we want to define T of X in such a way that the restriction of T to X0 is T0. But T0 is already defined on X0, and X0 is dense. So we can always find a sequence in X0 which converges to X. So we choose a sequence xn in X0 which converges to X. And clearly we can, the only way to define T of X is to apply T0 to Xn and to take the limit, because T wants to be continuous. To show that the limit exists, we observe the following. So Xn converges to X, so Xn is the Cauchy sequence in X0. Xn is a Cauchy sequence in X0. But we already know, and this was proved at the previous lecture, that a bounded linear operator takes Cauchy sequences to Cauchy sequences. So this implies that T0 of xn is a Cauchy sequence in Y but Y is a Banach space. And so the sequence converges. Let's denote the limit of the sequence by a little y. This is an element of Y. So now it's natural to define T as follows. T of x equals Y. But to show that this is well defined, we have to show that this limit doesn't depend on the choice of the sequence xn. Well, let's suppose that we take another sequence. Suppose that xn prime is another sequence in x0 which converges to x. So xn converges to x and xn prime converges to x. So this obviously implies that xn minus xn prime converges to 0. But T0 is a bounded linear operator. Equivalently, it is continuous. So if we apply T0 to this sequence, we conclude that T0 of xn minus T0 of xn prime converges to 0. And since this sequence converges to y, and the difference converges to 0, we conclude that T0 of xn prime converges to the same limit. The limit of T0 xn prime is the same element y. So this implies that this element y depends only on x. It doesn't depend on the choice of our sequence. So hence we have a map T from x to y which takes every element little x to the element little y defined by this formula. It's clear that this map extends to 0 because if little x is already in x0, then we can just take xn equals x. We can take the constant sequence. So this construction implies that T0 extends, that T extends to 0. Also, it's rather easy to show that T is linear. This is an easy exercise for you. Basically, everything follows from the linearity of T0 and from the continuity of the algebraic operations in norm spaces. And the continuity of the algebraic operations is the first exercise in exercise sheet 1. So T is linear and extends to 0. The final step, why is it bounded? Well, that's more or less clear because, again, if we look here, so T0 is bounded. So we have the following estimate. For each n. Now we just take the limit of this. The left-hand side converges to T of x, and the right-hand side converges to, this is a constant, and the norm of xn converges to the norm of x. And this is true for each element x in our space. So by the definition of the operator norm, we conclude that the norm of T is less than or equal to the norm of T0. But of course, it cannot be strictly smaller because T extends to 0. So actually, the norm of t is equal to the norm of t0. So this proves part 1 and part 2. Well, I didn't say anything about the uniqueness, but the uniqueness is clear from the density of x0. So the uniqueness of t follows from the density of x0. So this completes the proof of part 1 and part 2. Well, as for part 3, well, it's more or less the same as the proof of the boundedness of t. So suppose that t0 is topologically injective. We know that an operator is topologically injective if and only if it is bounded below. That is, there is a positive constant little c such that the following inequality holds. For each element in x0. And now we do the same. We substitute here xn, where xn is our sequence converging to an arbitrary element in X. Maybe let's denote this by some other letter to avoid confusion. For example, a little z. So now we take an arbitrary element x in the bigger space X. We choose a sequence xn which converges to X. So for each n, we have the following estimate. And now we let n go to infinity. So t0 of xn converges to t of x by construction, and xn converges to x. This inequality means exactly that t is topologically injective. And finally, if we assume that t0 is an isometry, then we just use the same argument. So little c0, a little c is now is equal to 1, and we have an equality here. So this will be an equality. So this is also an equality, and so t is an isometry. And this completes the proof. So this is very useful result. So every bounded linear operator defined on a dense subspace of a normal space and with values in a Banach space can be uniquely extended to the whole space X. Okay, let's now discuss completions of normal spaces. First of all, let's recall the definition of the completion of a metric space. This will be definition 1. Suppose that X is a metric space. Then, by definition, a completion of X is a pair, X tilde and J, where X tilde is a complete metric space, a complete metric space. And J is an isometric embedding of X into X tilde, an isometric embedding, such that the image of J is dense in X tilde. The closure of J of X is X tilde. So this is the standard definition of a completion of a metric space. So we want to give a similar definition for norm spaces. Now this will be definition 2. Suppose now that X is a normed space. By definition, a completion of X, a completion of X is a pair X tilde and J, where X tilde is a Banach space and J is a linear isometric embedding. J is from X to X tilde is a linear isometric embedding. Such that the image is dense. Well, I'd like to stress that definition 2 is not a special case of definition 1. Because here we assume that X tilde is a Banach space, not just a complete metric space, but this is a Banach space. So it carries a vector space structure such that J is not just isometric, but is isometric and linear. So definition 2 is a natural analog of definition 1, but formally it is not a special case of definition 1. So now the first natural thing to do is to show that this completion exists. Proposition 1. Every norm space has a completion. I mean, completion in the sense of definition 2. To prove this result, we'll use the well-known fact that each metric space has a completion in the sense of definition 1. I assume you know this from your course of calculus or topology. So we take a normed space. We take a normed space X, and we let X tilde and J be a completion of X in the sense of definition 1. So X is a complete metric space, and J is an asymmetric embedding onto a dense subset. So now we want to define a vector space structure on X, which extends on X tilde, sorry. We want to define a vector space structure on X tilde in such a way that J is linear. For convenience, let's identify X with the respective subset of X tilde. So we identify X with its image J of X in X tilde. So So each element little x is identified with its image in x tilde, so that x becomes a subset of x tilde. This is a standard convention to identify a metric space with a subset of its completion. So now we want to define a vector space structure on x tilde, which extends the vector space structure on x. So we take any two elements in x tilde, x and y, and we do more or less the same trick as in the proof of the extension by continuity theorem. Namely, we choose sequences. We choose two sequences, xn and yn in x0, such that xn converges to x and yn converges to y. In x, sorry. Now x is a dense subset of x tilde. And we define the sum of x and y to be the limit of xn plus yn. Similarly, for each number lambda, we define lambda x to be the limit of lambda xn. And finally, we define the norm of x to be the limit of the norms of xn. Or equivalently, this will be just the distance between x and 0. Of course, we have to show that these limits exist, and moreover that they depend only on x and y. And this is a more or less straightforward exercise for you. First of all, I recommend you to show that the above limits exist, and if we define the algebraic operations in this way, then x tilde becomes a vector space. And moreover, the limit exists and they depend only on x and y. So the algebraic operations are well defined, and x tilde becomes a vector space. And it's clear that it's clear from these formulas that J, the embedding J, is linear. Clearly, J is linear. So, modulo this exercise, this completes the proof. The exercise is rather elementary, but is a little bit tedious. But in fact, in a couple of weeks, we will be able to give another independent proof of the existence of a completion for each normed space, which doesn't rely on the existence of completions of metric spaces. And this second proof will be just a line or most two lines. So it will be very simple. Okay. So now we know that every metric space, every normed space has a completion. Let's now prove the following simple but fundamental property of completions. This is proposition 2. This is the so-called universal property of completions. So suppose that X is a normed space. Normed space. Y is a Banach space. And T is a bounded linear operator from X to Y. So let's draw a picture. This is X, this is Y. And let's also look at the completion of X, X tilde. So here we have the canonical embedding J, and T is an operator from X to Y. I claim, first of all, that there is a unique bounded linear operator T tilde from X tilde to Y, which extends T in the sense that this diagram is commutative. Moreover, the norm of T tilde is exactly the same as the norm of T. And finally, if T is topologically injective, or if it is isometric, then so is T tilde. So in other words, shortly, each bounded linear operator from X to any Banach space Y uniquely extends to the completion of X. The proof is just a simple application of the extension by continuity theorem. So we identify X with its canonical image in the completion and apply the extension by continuity theorem. Extension by continuity theorem. Okay, now by using this result, we can easily prove that the completion is unique in the following sense. This is proposition 3. The uniqueness of the completion. Suppose that X is a norm space. And suppose that we have two completions, say X tilde and J, and X hat and J prime. Suppose they are completions of X. Well, let's draw a picture. This is X, this is X tilde, and this is X hat. Here we have J and J prime. I claim that there exists a unique isometric isomorphism, a unique isometric isomorphism between X tilde and X hat, let's denote it by I. such that this diagram is commutative. So briefly, we can say that the completion is unique up to unique isometric isomorphism over X. Over X means precisely that the diagram is commutative. So in some sense, this isomorphism is canonical. It is uniquely determined by this diagram. The proof is a straightforward application of the universal property. First of all, we look at this picture, and we use the fact that X tilde is the completion of X. So by proposition 2, there exists a unique bounded linear map, which is in fact an isometry, a unique isometry I from X tilde to X hat, such that this diagram, let's denote it by 1, such that diagram 1 is commutative. That is, Ij equals J prime. Okay, let's now use the assumption that X hat is a completion of the same space. So we look at the same picture. This is J, this is J prime. So X hat is also a completion of X. And so we apply proposition 2 to the map J. So now we extend J to X hat. And we get a map from here to here. So proposition 2 implies that there is a unique isometry I prime from X hat to X tilde such that the second diagram is commutative. That is, I prime composed with J prime equals J. And now let's, so we want to show, to complete the proof, we want to show that I, or equivalently I prime, is an asymmetric isomorphism. So it is surjective. And to show this, we just combine pictures 1 and 2 into a single diagram, which involves only X tilde. So X tilde, and X. This is J, and this is J. So a natural question, does there exist a map from here to here which makes the diagram commute? The answer is obviously yes, and the identity map does the job. The identity map. But actually we have another candidate, namely I prime composed with I. Well, indeed, if we combine pictures 1 and 2 into a single picture, we easily see that this map, I prime I, also makes the diagram commute. So we conclude that both the identity map of X tilde and I prime I make this diagram commute. And now we look once again at proposition 2. Specifically, we look at the uniqueness in proposition 2. So since such a map is unique, we conclude that these maps are the same. So I prime I is the identity map of X tilde. And the similar argument shows that I composed with I is also the identity map. Similarly, I prime is the identity map of X hat. So these two properties mean precisely that I and I prime are isomorphisms. In particular, I is an isometric isomorphism. And this completes the proof of the uniqueness of the completion. In summary, if we look at the proof, we see that actually there is no functional analysis here. So this is a straightforward corollary of proposition 2. And in fact, this result, the uniqueness of the completion, is a very special instance of a general category theoretic fact, which states that if we have a representable functor on some category, then if a representing object exists, then it is unique. Okay. Another important property of completions is the functoriality. Proposition 4. The functoriality of completions. So suppose we have two normed spaces, X and Y. And suppose that T is a bounded linear operator from X to Y. So again, we draw a picture. This is T. This is the canonical embedding of X into the completion X tilde, Jx. And here we have the canonical embedding of J into Y tilde. I claim that there exists a unique bounded linear operator T tilde from X tilde to Y tilde. This is T tilde, such that the diagram commutes. So each bounded linear operator between normed spaces uniquely extends to a bounded linear operator between their completions. Moreover, the norm of T tilde is exactly the same as the norm of T. Part 3, if we apply this procedure to the identity map of X, then the result will be the identity map of X tilde. This is trivial, but this is important. Also, this operation is compatible with superpositions. If you have two composable operators, S and T, so we can compose them, and we then take the induced operator S T tilde, then the result equals S tilde composed with T tilde. So here T is bounded operator from X to Y, and S is a bounded operator from Y to Z. And finally, property 5, if T is topologically injective or isometric, then so is T tilde. Well, again, parts 1 and 2, actually parts 1, 2, and 5, readily follow from proposition 2, from the universal property. So to prove 1, 2, and 5, we apply the universal property, proposition 2, to the composition of T and Jy. So if compose these two operators, we get an operator from x to y tilde, and we just apply to this operator proposition 2. And we get the desired map T tilde. Finally, to prove properties 3 and 4, we just use the uniqueness part of proposition 2. So in particular, if we want to extend the identity map of X from here to here, then we have two candidates for this arrow, namely the canonical extension of the identity map of X and the identity map of X tilde. So by uniqueness, they should be the same. And similarly, if we have two composable operators S and T, well, for completeness, let me draw a picture. If we have S from X to Y, and T from X to Y, and S from Y to Z, then we have two commutative squares. This is the first one, and this is the second one. So clearly, the composition of S tilde and T tilde make the whole big diagram commutative. But alternatively, we can take the canonical extension of ST here. And so it should be the same as the composition of S tilde and T tilde by the uniqueness. So in the language of category theory, proposition 4 means that, well, at least parts 1, 2, 3, and 4 of proposition 4 mean that the completion is a functor from the category of normed spaces to the category of Banach spaces. And this functor is left adjoint to the forgetful functor which acts in the opposite direction. So we have the following natural isomorphism. Here, X is a normed space, and Y is a Banach space. So this is just a picture for those of you who are familiar with the language of categories. Those of you who are not familiar with this language just can skip this comment. It's not very essential at this point. Okay, now our next goal is to discuss quotients of normed spaces and some linear operators related to quotients. More exactly, we'll discuss open operators, coisometries, and quotients of normed spaces. So to begin with, let's define all operators, open operators, and coisometries. Suppose that x and y are norm spaces, and suppose that t is a linear operator from x to y. We say that t is open. That's the first definition. We say that t is open if it takes open sets to open sets. For each open set U in X, its image is open in Y. Of course, this is a purely topological property, which makes sense for any map between topological spaces. And the second definition, we say that T is a coisometry. A coisometry if it takes the open unit ball of X, this is our notation for the open unit ball, onto the open unit ball of Y. We now have the following proposition, which gives several characterizations of open operators, and which in particular relates open operators to coisometries. So I claim that the following conditions are equivalent. Condition 1, T is open. Condition 2, there is a positive number R such that the image of the open unit ball in X contains the open ball of radius R. And property 3, there exists a positive constant C such that for each element y in Y, there exists an element x in X satisfying the following conditions. First of all, T of x equals y. And second, the norm of x is less than or equal to C multiplied by the norm of y. In other words, condition 3 means that T is surjective in a rather strong sense. So each element y has a preimage, that is T is surjective, and moreover we can always find a preimage in such a way that the norm of this preimage is not very big. So it is bounded by the norm of y up to a suitable multiplicative constant. Okay, it's more or less clear that 1 implies 2. Because if T is open, then the image of the open unit ball is an open set containing 0. So it must contain a suitable neighborhood of 0. And that's it. This is precisely condition 2. Let's now show that 2 implies 3. So we take an arbitrary element in Y, or more exactly, we take a non-zero element in Y, and we define another element, Y prime, by the following formula. So we multiply Y by a suitable number in such a way that the resulting vector Y prime, the norm of this vector is exactly R divided by 2. So the norm of Y prime is R divided by 2, and so Y prime belongs to the open ball of radius R. And this ball, by assumption, is contained in the image of the open unit ball of X. So there is an element X prime in the open unit ball of X such that Tx prime equals Y prime. And now we define X, little x, by the following formula. So we multiply X prime by the inverse of this number. And so this equality implies that Tx equals Y. And also the norm of X is less than or equal to this number because X prime sits in the unit ball. So the norm of X is less than or equal to 2 over R multiplied by the norm of Y. So in other words, we have condition 3, where the constant C is 2 over R. Okay, so 2 implies 3. Finally, to complete the proof, to show that 3 implies 1, it is convenient, first of all, to observe that 3 implies 2. This is almost clear. We just take, which I define R to be 1 over C. So if condition 3 is satisfied, and if R is 1 over C, then clearly we have this inclusion. So for each element in here, we can find a suitable preimage, and the norm of this preimage will be strictly smaller than 1. So 3 implies 2. And finally, we show that 2 implies 1. So we take an open set, U, in X, and we take an arbitrary point, little x, in U. To show that T of U is open, we have to show that T of X belongs to the interior of T of U. So this statement means exactly that every point in T of U belongs to the interior. In other words, T of U is open. Well, okay, so X belongs to U, and U is open. So we can always find a ball centered at X, which is contained in U. In other words, there is an epsilon, there is a positive epsilon, such that the following set is contained in U. So this set is exactly the epsilon neighborhood of X. This is the epsilon neighborhood of X. Okay, now we apply T. And we conclude that T of U contains T of X plus epsilon multiplied by the image of the open unit ball. But the image of the open unit ball, by assumption, contains the open ball of radius R. So this contains the open ball of radius r, and after we multiply it by epsilon, we get an open ball of radius epsilon r. And this is a neighborhood of T of x. This is a neighborhood of T of x. So we have proved that every point in T of u is in the interior, and so T of u is open. And this completes the proof. As a corollary, we see that each coisometry is an open map. Because by definition, a coisometry clearly satisfies condition 2. So it is an open map. And condition 3 implies that each open map is surjective. Each open linear operator between normed spaces is automatically surjective. Okay, that's all for today. And at the next lecture, we define quotients of normed spaces, and we find some relations between quotients and coisometries.